Welcome everyone to today's explainer. So have you ever stopped to wonder what makes code truly good? Think about it. If I write a program and you write a program to solve the exact same problem, how do we actually know which one is better? Is it just about which one finishes first? Well, the foundational question of computer science isn't just about whether your code works, but how efficiently it runs, completely regardless of the physical hardware it happens to be sitting on. Today, we're going to master the logic of algorithm analysis, and we're going to do it by putting a microscope on literally one of the most fundamental building blocks of all programming, the for loop.
Our roadmap for today looks like this. First, welcome to algorithm analysis. Then, the anatomy of a for loop. After that, counting our operations, scaling up with asymptotic growth, and finally, big O and ignoring constants. We're taking a journey today from a single line of code all the way up to the abstract mathematics of computer science. So let's jump right in.
Section 1. Welcome to algorithm analysis and the need for universal measurement. Let me ask you all a question. How can we objectively measure code speed if your laptop is a brand new, top-of-the-line machine and mine is, say, 5 years old?
If we just use a stopwatch, well, your code is probably going to win, even if my algorithm is technically designed better. Measuring raw, actual time is a total trap for a few reasons. First off, execution speed heavily depends on your specific hardware. Second, the structural efficiency of the program itself obviously matters. Third, the quality of the compiler translating that code varies from machine to machine. And fourth, even the current system load, like, if you have 50 browser tabs open in the background, that's going to drastically impact the actual time it takes to run your code. Because these physical conditions fluctuate so wildly, the solution isn't to measure seconds. We absolutely have to evaluate algorithms based on their relative CPU time. This is what we call time complexity.
Before we dive into the math of time complexity, let's distinguish between two really common tools we use to repeat actions, the for loop and the while loop. It's kind of like doing household chores. A for loop is used when you know in advance exactly how many times you need to execute a block of code, like wash exactly 5 plates. You know the iterations. A while loop, on the other hand, is used when the iterations are unknown. It just runs until a specific condition becomes false, like keep washing until the sink is completely empty. Today, our primary focus is the for loop because its predictable, countable nature makes it the absolute perfect starting point for our analysis.
Moving to Section 2, Anatomy of a for loop, the micro view. Now that we know we need to measure relative time, let's zoom in on the absolute workhorse of programming to see exactly where time complexity originates. Okay, let's actually look at the code here. Since we already established we can't just use a stopwatch to figure out the running time in seconds, we have to estimate it. How? By counting the number of basic or primitive operations that the algorithm performs. Take a look at that middle line. For int I equals 0, I is less than n, I++. To really understand the speed of this entire algorithm, we have to understand exactly what that single line is asking the computer's processor to do.
So, here is the precise step-by-step cycle that loop goes through. First, we initialize a variable, setting I equal to 1. Second, we check the condition. Is I less than or equal to n? Third, if that condition is true, we execute the block of code inside the loop, like printing the value of I. And fourth, we increment the variable, bumping I up by 1. It's basically a continuous 4-step engine. By anchoring your understanding to this exact cycle, you see what the computer is actually executing behind the scenes. Oh, and as a quick aside, this structured cycle is also where we can check loop invariants. Those are relationships among variables that absolutely must remain true at the start of every iteration to ensure our algorithm is actually solving the problem.
All right, Section 3, Counting our operations. Step-by-step breakdown. It is time to do the math and count these primitive loop steps across an entire execution.
Let's trace a loop where our input size n is exactly 5. As our variable I increments from 1 to 6, notice what happens. The condition checks as true 5 times, but, and this is key, it must check a 6th time, which finally evaluates to false just to terminate the loop. Meanwhile, the block itself actually executes and prints the number exactly 5 times. This is vital to grasp. The loop checks the condition n+1 times to know when to stop, but it only executes the internal statement n times.
So, if we take those n+1 condition checks and add them to the n block executions, what do we get? A step count of 2n+1. This gives us a runtime function, representing the number of operations needed to execute the algorithm. Because the leading term, the n, has a degree of 1, we call this a linear polynomial runtime. Basically, for every single item you add to your data pool, the operations required grow in a straight, predictable line.
Part 4, scaling up, asymptotic growth, and dealing with massive inputs. What happens when our algorithms get much more complex and our data grows massively? I mean, a simple linear 2n plus 1 is easy to visualize, but real-world programs handling databases are so much heavier.
Take a look at this more complex time complexity function. T of n equals 15n squared plus 45n. Imagine an algorithm that requires this specific number of operations to process n items. When n is small, say you're just sorting 5 or 10 items, it really doesn't matter. The time difference is basically microscopic. But as the input size n grows, the dynamic between these two terms completely shifts. This is what we call asymptotic growth.
Now, what's really fascinating here is what happens as n scales up. When n is just 1 or 2, the 45n part is actually the bigger number. But scan down to where n equals 1 million, the 15n squared term has become an astronomically massive 15 quintillion. That's insane, right? It completely and utterly overshadows the 45n term, which is barely a blip on the radar at just 45 million.
Let that number sink in for a second. If you assume these operations take about a microsecond each, for 1 million items, this algorithm would take 173 days to run. 173 days. This completely drops the mic on why algorithm efficiency matters. It's not just some theoretical exercise for your midterm, it's literally the difference between an app loading instantly and a program taking nearly half a year to process your data.
And that brings us to Section 5, Big O and Ignoring Constants, the golden rule of analysis. How do computer scientists handle these massive numbers? Well, we abstract away all the noise. We need a mathematical shorthand to communicate this massive growth efficiently.
And this brilliantly illustrates our core lesson for today. For large values of n, the value of the time complexity function is almost entirely determined by the largest term. Because 15n squared is so much bigger than 45n at a massive scale, we say that 15n squared asymptotically dominates 45n. This lets us just drop the 45n entirely when we evaluate the algorithm's behavior. The smaller term just doesn't mathematically matter enough to care about.
So, the absolutely crucial point here is why we ignore small factors for large input sizes. Because different computers differ in physical speed by a constant factor anyway, we don't just drop the lower-order terms, like 45n, we also drop the constant factors, like the 15. We strip the function down to its absolute purest form. 15n squared simply becomes O of n squared. This is big O notation. The golden rule is we ignore the small stuff, the lower-order terms, and the constant multipliers to clearly see how the algorithm behaves as input sizes approach infinity. This lets us easily rank algorithms, knowing definitively that an O of 1 algorithm is faster than an O of n algorithm, which is inherently faster than an O of n squared algorithm, regardless of the physical laptop it's running on.
Which leaves us with this final, kind of provocative thought. If big O notation teaches us to ignore the small, constant physical speed differences of hardware in our theoretical math, what actually happens when our massive algorithms push those physical hardware limits to the absolute brink? Does memory space run out before time does? Can we ever truly separate the elegant math from the physical machine? Think about that next time you're writing a simple for loop. Thank you for joining this explainer. Keep learning, and I'll catch you next time.